Right, welcome back. It's taken quite a few minutes for us to actually set this up, so what I'd like to do is take some time out to explain what we're doing, and why we're doing it, and how we're doing it. We're actually testing Coil-On-Plug. This is one of the exact coils fitted to this vehicle. They often give trouble. The advantage is that you can isolate the coil problem to one cylinder and therefore change just the one unit, but we need to be a little bit more objective. We need to prove the coil's faulty in a technically intelligent way. We are denied access to actually using an inductive pickup, and often using an inductive method through the body of the coil creates a lot of interference. So what we've done to this coil is a voltage and earth supply. In this coil is the power stage, so the actual current is controlled within the coil, not the computer. That's to our advantage, because to switch the power stage on and off there must be a digital control signal trigger. So we're setting channel 1 blue to that digital control pulse from the computer. We're running live now, by the way. That stabilizes the scope image, so I've done several things. I've set a time base at 1 millisecond, 1,000th of a second per division. I've set up the triggering pulse with a negative edge trigger, and that trigger indication means that it's been stabilized on the screen with a repeat trigger. So in other words, every time a successful event takes place, the screen update also updates the new information. I've then connected current to either the power or the ground circuit. It does not matter which. And you'll see there's a tremendous amount of current in this type of coil. It's pulling just shy of 16 amps. About 15 amps is about the correct level. So what does this tell us? Well, it tells us that the coil is being triggered by the computer. That's the first good news. Because we've got 16 amps, I now know the power supply and ground to this particular coil, or to the circuit that we're testing, is actually correct. But what about the burn time? What's happening there? Now the way we're going to actually pick this up is to use, in fact I'll show you the actual probe. There's nothing special about this at all. I'm simply using an extension probe, and I'm going to probe around the coil to obtain the best possible image. Now I'm going to have to lean across camera a little for this, but bear with me. And what I'd like to do is introduce this now across the coil. Now the essential thing really also to mention here is that the sensitivity of this has been set to 200 millivolts because we're using the inductive reactance of the coil to introduce the signal into the probe. We're not connecting to any cables. We're only connected around one cable for current and into one circuit for the actual triggering pulse. Now if I introduce this to the coil, and I'll try and freeze the image on the screen, which I think I'm just about to do. I'm holding that now just on the top of the coil, freeze the screen. Now you can see quite simply we now have 3 events to view. We have the triggering event, and you can see that through inductance the reaction in the green probe shows the coil being switched on. So the initial onset of current, switch on spark, has taken place. The charge phase of primary, a little bit of resonance here when the charge has been turned off, because clearly here's your current rise, current interruption. That's the instant that the coil induces high voltage into the secondary circuit and therefore down to the plug, because obviously that takes place within that physical environment. There's no HT lead as such. But this is the event we really want to see. This is a reflection of the spark time, and this is the point at which the spark depreciates, diminishes if you like, within the coil winding. There's always some residual energy, and that causes a resonance in the coil, in the secondary winding of the coil. So the bit that we're actually interested in here now is the actual burn time, spark duration, and we can estimate this now very accurately between those 2 points I've just mentioned, which is the collapse, the inductance process, the induction process at the coil induction period, which is there, and the coil ringing, the oscillation, which is here. and the delta time between the two is 1.8 milliseconds, which is absolutely spot on for this particular system. 1.8 thousandths of a second, and indeed, just with rule of thumb measurement, you can see here that the zero baseline in milliseconds, 1 millisecond per division, 2 milliseconds here, so it's near enough simply to estimate it. If you want an accurate measurement, bring the two cursors across, measure the delta differential, and then we have a very accurate measurement of the burn time of that particular coil. All we need to do now is transfer the test to each coil and repeat the test. If you really wanted to question the coil, I don't recommend this, but it's always possible. If you suspect the actual coil's faulty, you can transpose one coil into another cylinder and conduct the test using a different component. But really, what we see here is quite conclusive. We can measure current, power grounds like we did in the original filming. Burn time done by the process of inductance simply by touching the probe. Get the best image on the signal, freeze the screen, and then review the data. Extremely successful, it's worked well for us. It does not remove the need for physical examination, that's quite important, so preparation is something I never underestimate. Examine the plugs, examine the physical condition of the coils, look for signs of tracking, water ingress, etc. Correct that first before conducting electronic tests. But an entirely satisfactory test.